Hi, everyone. So let me tell you what this is about. So this is going to be the first half of this missing lecture from when I was sick a few weeks ago, and we still have some material to cover. So I'll be catching up on kind of from some chapters that we did, like the last extra section of it. So all of this is still exam material, but it's now a little bit out of order. So I can tell you what the order that matters is. And it is the following. Up, give me a second. Okay, it is the following. So you should watch this lecture before the exam, okay? And after we talked about the stationary 1D cases, so at least after lecture 18. You can also watch it at the end of the semester, it doesn't matter. None of the following lectures will depend on this. So there's two halves of this missing lecture. The first one is about the this stationary states of the 1D box, but the finite case now. And then the second one will be about the harmonic operator. So again, you don't need to watch this lecture now to keep following the lectures if you're doing them in real time. So 27 will not depend on this 26. That's 26A and 26B. So the good news for you, less so for me, is that I just streamed the whole lecture to find out at the end that I had been muted all along on Zoom. So that was fun. This is good because now you have the lecture. Well, now I'll be much faster because I already have all the slides written. If I go over some steps a bit faster than usual, what you can do is just, stop the video or slow down the video or so on. Okay. Again, where are we? There we are. Good, I'm definitely not muted. I will just double check that I'm live now. Before we start. So again, what we do now is to talk about, okay, I am, good, I just checked YouTube. Okay, good, so we'll solve this and we could solve it in the usual way, but in fact, we're gonna do it in a more fun way that you can apply also in other cases, which is by introducing a new operator and seeing how it can help us solve the problem. So I'll explain all of this. So let's just recap where we were last. So we're looking at Hamiltonians in 1D of this form, right? Which has some potential v of x. And then we looked at the very, very simple cases where this v of x has kind of flat zones, right? It could be something like this. And then we said, well, in regions where it is constant, then we solve the Schrödinger equation for stationary states, meaning H psi E equals E psi E. And then we saw that there's two options. Either this energy of the state is higher than this V0 or it's lower. If it's lower, we saw that the wave function is a sum, so a superposition, a sum of exponentials one way or the other. So there's an exponential that goes like this, and there's an exponential that goes like that. And then depending on the conditions of the problem and normalization conditions, we sometimes set one of these to 0, right? Okay, and this B coefficient depends on the mass of the particle because the mass is here, on H bar because it appears in the effect of P in the wave function, right? And then the potential in this region and the energy that we're considering. And if the energy is smaller than V0, then it is actually, you can see it as a superposition of a wave traveling to the right and a wave traveling to the left, right? And again, this K, which tells you how fast the wave oscillates, also depends on this difference of energies. Okay, very good. So this is what we did last. So what's the case of the square well? This is a region where the potential just has this form. So it has some region finite that is 0, and then around it, it has finite value, v of x. So it has some region that is finite 0, and everywhere else is this v0, larger than 0. Okay, very good. I need some water. Okay, so then what's the general solution for this case before we look at continuity conditions? In the middle of the box, we have, as per usual, a wave oscillating to the left and a wave oscillating to the right. So there we are, the right and to the left, with some coefficients that we don't know yet. And outside, we could have here these two exponentials, there and there. But this one diverges, so we cannot normalize it. So it's not a physical solution. We only have this. And outside, we only have this. This for the cases where the energy is smaller than V0. So you can think of it as a particle that is kind of classically, it's kind of bouncing around here inside the box. And, you know, with a small probability it can be found outside, but this probability decreases very, very quickly, exponentially. So it's exponentially suppressed. So this is why they're called bound states. Bound states. Because they're kind of bound in this region, right? And in the lab, we can actually create potentials that are more or less like this. Okay, good. So we still have all these coefficients, which are all free. And what we do with them, so we could solve them in the usual way like we did for the scattering barrier, but we're going to introduce a new tool, which in fact we've already used for the hydrogen atom, if you're there for this lecture. So here it is. Oh, let me move this here. Okay, good. So what is the new tool? Is the following. We find an easier operator than the Hamiltonian that has very easy eigenstates that we know. Then we see that we prove that it commutes with the Hamiltonian. And this tells us that, well, if they commute, then they share eigenstates. So now we already get some restriction into the eigenstates of the Hamiltonian. And then what's left is still to find all the eigenvalues, so the energy values, and the exact form of the eigenstates, because this operator may only give us some constraints. This, if you already watched the lecture on central potentials and angular momentum and the hydrogen atom, it's exactly what we did. So we had a very complicated Hamiltonian, but we had simple operators, the angular momentum operators, which we saw they all commuted with the Hamiltonian, right? So then we said, well, we know what the eigenstates of these operators are. They were the spherical harmonics, right? So now we know these are energy eigenstates. There was only this radial function that was left to compute, right? And so the whole work of finding the eigenstates reduced to, instead of caring about the whole state, just caring about the radial part of the wave function. And then we did a bit more work to find the exact eigenvalues and so on. So that's exactly the same setting, except it's going to be much, much, much easier because, you know, this potential is much simpler than the potential of the hydrogen atom. So we introduce an operator called the parity operator. This is in 1D. You can introduce a similar thing in 2 or 3 dimensions if you want. So what it does, if you write it in its matrix form, operator form, is it takes x and it maps it to minus x for all x's. So we'll see that what it does in practice is to check if a wave function is symmetric around the 0 or antisymmetric or something else. So I'll tell you what this exactly means in a bit. So let me just write here what the claim is. So the claim is that this operator only has 2 eigenvalues, which are +1 and in this case, the eigenstates are all the even wave functions, which we'll get into, and -1, for which they're all odd wave functions. And for other functions that are neither either even or odd, these are not eigenstates of this operator. Okay? So that's the claim. We're going to prove it in 3 steps. First, we're going to see that for even wave functions, we get +1. Then we're going to see that for odd, we get -1. And then we're going to prove that these are the only 2 eigenvalues of the operator. So let's start. What's an even wave function? This is when psi of x is the same as psi of -x, okay? Meaning that it's symmetric around this point x equals 0, right? So if I put a mirror here, for example, you get the same function as if the mirror was not there. Okay. So then we need to show that psi, this operator P for parity. So it's kind of a curly P, not to confuse with the momentum operator, applied on a wave function. It's going to give us 1 times the wave function, right? This is the goal, to give us 1 times the state again, to show that it's a negative state. Okay, so we just do it. So what is P? I already wrote it before. It's going to be this. I use a different integration variable, this x prime, so as not to confuse with this one. This is just an arbitrary expansion of any state, psi. So now we have these two integrals, and then what we have inside, so we have this, cat goes there, and then this to give us an inner product, and then this number, which is the wave function, is left there. It's just a number, so you can go to the right. Okay, now we have this inner product. We know this is a Kronecker, sorry, the delta function of Kronecker. Okay, which means we can get rid of one of these integrals. So we get rid of x prime. And what we're left here is this term here with x prime equals x, and then this number again. Okay, now what we do, just for simplicity, just to make sure we really see it, is we just do a change of integration variable from x to x prime. So here you'd have to have minus, you change the integration limits, but because they go from minus infinity to plus infinity, it's the same. X prime equals minus x, so here we get x prime, and here we get minus x prime, right? So up to here, it was completely general for any state, any wave function. And now we use the fact that it's even. So we have this condition. So we can just replace this with psi of x prime. Right? And now we get this, which is exactly the original state. So we have the original state, and we can put a 1 here. We proved what we wanted. So we proved that the parity operator acting on an even state gives us back the same even state, symmetric state with the eigenvalue 1. Good. So now we need to see odd wave functions, and I did not draw here what they are like, but let's say, for example, something like this, right? That if psi of x equals minus psi of minus x, which means if you put a mirror here, you have in addition to, you have to flip plus and minus to get the same function again. It's antisymmetric. It's odd. Okay, so we do the same thing. We apply P to thing, and we can come back, we can bring back this simplified expression, because up to here it was an arbitrary wave function. Okay, so then we have psi of minus x prime, and then the cat for x prime. And now we use the fact that it's odd, so we replace this with minus the wave function, and this minus can come outside here, and then we have inside again the state, right? So we get minus tag dx psi of x, right? So that's -1 times this. Okay, so it's proven now. We prove the two first parts, that for any even wave function, we get eigenvalue 1. For any odd wave function, we get eigenvalue -1. Now we need to show that it is that these are the only two possible eigenvalues, and that's very nice. So we're going to show that this matrix is both Hermitian and unitary. Another examples of Hermitian and unitary matrices are, for example, the Pauli X, Y, and Z operators. I don't know if you remember, we can both use them as unitaries for evolution and as observables. So for observables, meaning that they're Hermitian, and evolution, meaning they're unitaries. And they all have eigenvalues plus and -1, right? The reason for this is that if it's Hermitian, then all the eigenvalues must be real. If it's unitary, all the eigenvalues must have norm 1. So they must be of this form, just a phase. And if you put these two conditions together, it's real with norm 1, then there's only two options, -1 and 1, right? So we just have to show this. And it's going to be very easy. So first we look at what is the transpose conjugate Pythagoras of P. So here's P. We take the transpose conjugate. Note that this is just a sum. So the transpose conjugate of a sum is the sum of the transpose conjugate of the individual elements. So the sum stays the same. And then what it does is there's no complex number here. So all it does is to flip the bras and the cats. So there we are. But then these two are the same integral. And if you want to see it really explicitly, you can change variable again, right? Define an x prime equals minus x. And then you get exactly the same expression as up here. Okay, so that's P again. P equals Pythagoras, so definition of being Hermitian. So the other thing is to see that it's unitary, which means that Pythagoras P is the same as P Pythagoras, which is the identity. Okay, just a second. Grab some more water. Okay. So then we do this. Here's P. Here's Pythagoras, which is the same as P. So these two numbers are going to be the same. But I already wrote them in the nice form. So we use different integration variables, x and x prime, so that we don't confuse them. So then we get these two integrals. We have this minus x term, ket, then this bra and this ket give us this inner product, which is just a delta again. And then we have here the minus x prime, right? This means we get rid of one of the integrals. So then you get the integral over x of minus x. And you can do again the same trick, right? Just change the variable to flip the signs if you want, right? So if I had minus here or plus, because it's the integral over all x, it's the same. And that's just a definition of the identity matrix for 1D continuous systems. So we've shown it's Hermitian, we've shown it's unitary, so we know that it only has eigenvalues -1, +1, and we know what they are. Right. Okay, good. Sorry, I dropped some water over the next lecture. Not good. So we have this. We need one more ingredient before to show what we want, which is that it commutes with the with the Hamiltonian, and that's looking at how this operator parity acts in the momentum basis, right? Because the Hamiltonian is a momentum operator there. Okay, so let's see how it acts on the basis element, little p. And we say, okay, well, we can put an identity here for free. And we can write this identity in the x basis. So now this p can go inside the sum, right? So we have px on one side, and on the other hand, we have like these two. Brian cat give us an inner product. Px, by definition of p, is minus x vector. And this inner product between x and p, well, this was from the, so remember this p is the parity, and this p is the momentum basis. So this was from the very definition of position and momentum basis, what this inner product was, right? It was this exponential divided by this constant. This is what we did a long time ago. Okay, so then we just rewrite this. So we have this constant goes here, and then we have this number inside here, and then here we got the minus x, right? Okay, let's, just to be super clear, let's change variables again from x to x prime, that's minus x, to see what this looks like. So now we have x here, and then we have this exponential minus p x prime I divided by h. And if this is familiar, this whole thing is because this is exactly the definition of the momentum the momentum eigenstates, yes, momentum basis element, except that to get p, you'd have a plus sign here. So if you have a minus sign, what you get is minus p. Now, this is very nice, because we saw that p acts in the momentum basis in the same way that it acts in the position basis. Eh? That's very curious. That's normally not the case for most operators, right? They act very differently in position and momentum basis. But here, when you have the parity applied to a momentum eigenstate, you get minus that momentum eigenstate. Okay? So that's very nice. Conclusions, it's here. So this is what I just said, which means you can also expand the parity in the momentum basis in the same way that we did for the position basis. So we just put a minus p here. Okay, now we have all the ingredients we need to show that this parity commutes with our Hamiltonian. Okay, how do we show it? All right, let's replace the Hamiltonian. This is the kinetic energy and the potential energy. Now the commutator is linear, so we just have this coefficient times this commutator between momentum square and the parity, and then we have this. If you want the whole thing to be zero, either they cancel each other out, or they're both zero. They're both zero in this case. So we're just going to show this. So first we look at the first one, for P. And for this, we're going to use just the simplest representation of the momentum operator, which is, we can write it in its eigenbasis, in the momentum eigenbasis, and then P is just dP, the number P, and then the projector into the momentum basis element P, right? And this is true also if I have any power here, then I just get any power here, right? We saw this a long time ago when we first introduced position momentum. So this lecture is a nice wrap up. Okay, so then we write this. What's the definition of the commutator? P square, sorry, momentum square parity minus parity momentum square. Okay, so we just write here. Here's momentum squared, like we did there, and here comes the parity minus the parity, and here is the momentum squared. Now, note that here, this is a sum, this is a number, so this parity operator can go inside there, as before. Okay, in the first term, we have this element here. So, sorry, it's the parity acting on this bra. You know, parity is the same as parity dagger. So what we get here is minus P. And here we have again the parity acting on this P, so we get here minus P. And now they already look very similar, except that here I have P minus P, and on the right I have minus PP. Okay, good. So we do the same change of variable as before so that we can more directly compare the two. So we get P prime is minus P, so that here we swap them, minus P prime, P prime. And then here we have minus P prime squared. Okay. On the right, nothing changes. And now, of course, what matters here is that this function p squared is actually is even again. So minus p squared is the same as p squared. So then these terms are exactly the same, right? So they cancel out, we get 0. So this term is 0 here of the commutator. We need to do now this term here. So we do it first for a very general Hamiltonian, and it's exactly the same, except in position basis now. Good, so it's v of x p minus parity v of x. V of x has this form, right? We saw before many times. So it's diagonal in the position basis. Great. Here's the parity. The parity here can go inside the integral. This v of x is just a number. Good. So then parity acting on this bra gives us minus x, and the parity acting there gives us minus x. Perfect. So now, yeah, we have this again, and it's the same situation as before, right? They look very similar, except here we have x minus x, and there we have minus xx. So just so we can compare them better, we do again this change of variable just for the first integral. Here's a change of integration variable. So now we have minus x prime, and here we have a v of minus x prime, right? And here v of x. So now we can even combine these two integrals in one. We could solve it directly by just saying, no, wait a moment. But let's just combine these two integrals into one. So we get minus xx, and then here, v of minus x from here, minus v of x, right? We can do this because these elements have the same form, right? They are the same state, same projectors. Good. And now, only now, we use the fact that, well, we choose our coordinate axis very cleverly, such that our v of x was symmetric around the 0 point, right? So v of x is actually an even function. So then this term is 0, so the whole thing is 0, right? So whenever you have a problem where it looks like there could be some symmetry, you just can choose your coordinate axis very nicely to make the symmetry really precise, so that then you can apply this kind of tricks, right? Then you can define the parity operators and see that it commutes with it. Great. So this is very good. Why? So now we know that the Hamiltonian commutes with parity, which means that the eigenstates of the Hamiltonian must in particular be eigenstates of symmetry, of parity, which means they can be symmetric or antisymmetric. Symmetric are states that have even wave functions, position wave functions, and antisymmetric, those that have odd position wave functions. So normally, just in terms of terminology, one says symmetric or antisymmetric for the states that are vectors, and even and odd for the actual functions. Doesn't matter too much. So let's go back to this, the general solution that we had before. This means that we can simplify all these coefficients a lot, and that's why we did all this. So let's look first at the symmetric case, then we look at the antisymmetric case. So in the symmetric case, we know that psi of x for stationary states must be psi of minus x, which means, first of all, that this coefficient must be the same as that, so that outside the box it's symmetric. And inside the box, this coefficient must be the same of this. But if they are the same, then we can write it, the whole thing, as a cosine, because remember, cosine is just e to ikx plus e to minus ikx, right? Which is what we have here. If these coefficients are the same, they then can come outside. and they're kind of absorbed all by this new constant. Yeah. This new constant that we put here, we don't know what it is yet. Good. And that's it so far. So what does it look like? It can look, for example, like this, right? So here's a poor expression of a poor drawing of the wave function, where it's a cosine. Yeah, so it's really bad because it should be 1 in the middle. This is bad. Right, the cosine is symmetric, but something like this. Okay, let me erase it actually. And we don't know anything about K. Mm-hmm. I don't know, something like this. But in the middle, cosine of 0 is 1. Yes. Yes, yes, yes. Okay. So they look like this. We still have some freedom in this case. And we still have some freedom in this A and B. So what we do is the usual thing of checking continuity conditions where, well, in this points A and minus A, where they change. But because of the symmetry, this will be redundant. We only need to check one point A because the conditions are going to be exactly the same. So what are the conditions at x equals A? First, the wave function must be continuous, right? So on the right, we get A e2 minus b x is A. Inside the box, it's this. And because now the potential is finite, then the first derivative must also be continuous, right? This is the other continuity condition we looked at. So we derive this exponential, we get minus b because A is x, right? And here the derivative of cosine is minus sine times the constant k. So now this gives us two equations for two variables, so this can be solved plus the normalization. But actually, yeah, if you think about it, so we have these two variables, right? A and B. One of them is given by the normalization. And then we have two extra equations here. Right? So we have more constraints than it looks like we have variables. But what we forgot is that there's an extra variable that's hidden here inside the K, I think. So let's have a look how we define this K and B. Let's just recap. I'm there. There we are. So K is inside the box, depends only on the energy because B0 is 0, right? It's this. And B is outside the box. It depends on B0 and on the energy. So meaning that we have another variable here that is the energy of the particle, right? That is encoded here because the mass of the particle we know, h bar we know, V0 is given by the setting of the problem, but the energy is still free. So now in fact we have three equations. So we have this, and then we have normalization. And we have three variables. So we have A, we have B, and we have E that is hidden inside here inside the B and the K. So we could plug the three conditions into a computer and solve it. But given that all these problems were first studied before there were computers, at least computers that could do any kind of symbolic calculus, then people had to think of clever ways to extract this information from the equations, right? Even though it's all there. Okay, so one clever way to do this, which again, in retrospect, it makes some sense, is like we have these two equations, 1 and 2. If what's on the left is the same as if what's on the right, then if I divide the two equations, 2 divided by 1, they must still be the same on the left and the right. So just to make it clear, this is like I have 2 on the left, 2 on top, 1 on the denominator. So here's the second one with the derivatives, and here's the first one, right? Okay. So simplifying this, so all of this cancels out, these cancel out. So we get this nice equation here. So B divided by K must be the tangent of KA. And this is now a constraint that is not on A, or it's not on this A or B. It depends on the length of the box A, which is given. And these two things depend on the energy, right? So what this is now is a constraint on the energy, and in fact is a constraint on the energy values allowed for stationary states. This will tell us that our Hamiltonian does not have a continuous spectrum, but instead it has a discrete spectrum. So how do we compute this exactly? Well, you can go and replace what B is, that's square root blah blah blah, and what K is, and K is here, and you can solve the equation exactly. But before that, you can do this at home. I will not ask you in the exam. What we can do is just we plot this function here and we plot this function there, and we see where they meet. So this is tangent, more or less. Yeah. So that's this part here, depending on this variable K or KA. And this is B over K, essentially, right? So this is that. So on the axis you have K, and just to make things look a bit nicer, the tangent, we know where this point, or where these points are of the tangent. We just scale it by A, it doesn't matter. Okay, so we have the tangents going up, and then we have this line coming down, right? Which is this. So the points where they meet, these are the allowed values of B and K. So in this point, you can see what K is, and from here you can see what the energy is. So then now we have discrete allowed values of energy for the symmetric energy eigenstates. Great. Now we need to see the antisymmetric case. It could be that the antisymmetric case now gives us a bunch of continuous solutions, and we don't have the discretization of energy, but no, it's more or less the same. So what's the antisymmetric case? Well, now we have this condition to fulfill, right? So meaning that this value must be the opposite of this value. And here we need to have this exponential in one direction with the minus the sign of the exponential in the other direction. And this gives us essentially a sign. So we have sine of kx, which is the odd function, up to some constant b. Typo here. Okay, good. Right, so just to clarify again. Right, so we need to have this and this having opposite signs. That's what we did. And then we need to have this and this having the same value and opposite signs. And when this happened, we just factor them out and we're left with that, and that's the sign. Okay, good. And then we look again at the continuity conditions. So we do exactly the same thing. So the function must be continuous. And the first derivative must also be continuous. Derivative of sine is cosine. So then we get, what we get is this solution here. When we derive the two, we do exactly the same, and we get this condition. B over K equals minus the cotangent, which is 1 over the tangent of Ka. Good, good. So this is the antisymmetric solutions, and these were the symmetric solutions from before. So now we plot them all together in this plot. Again, this thing is the thing that goes on the left. It was the same on the other side. This is a tangent. So these are the even solutions. These points are the even solutions. And now we have this minus cotangent, which looks extremely similar. Right? which gives us some extra points. So these are all the allowed values for energy. Turns out that as we go like this, the energy increases. So at some point, it's no longer a valid solution, because why? Because remember, we had this whole condition that energy should be smaller than V0. And if you continue going here, at some point, we'll reach the point where energy is the same as V0. So then we're no longer in the setting of bound states, so we cannot apply all this machinery. So what we found out is the following. One, there's a finite number of bound states that are energy eigenstates. Two, the allowed energy values for bound states are discrete. Three, there can only be even eigenstates, symmetric eigenstates or antisymmetric eigenstates, and they really correspond to this. So the first one, this is going to be the ground state, is even, the next one is odd, the next one is even, the next one is odd. Okay. The number of solutions depends on what? Well, it will depend on the factors of the problem. So on V0, which is this height of the potential, and A, which is the length of the box. Because for energy larger than this, then we're again in the scattering states, then all energies are possible, and then you just have these waves, right? Well, which change here. Yeah, these kind of waves going one way or the other, but then you have again a continuous spectrum. And what the wave functions look like is like, the first one is a cosine that only has one cycle, doesn't get exactly to 0 because this potential is not infinite. So there's a little bit of energy left. And then it kind of decays exponentially. Right? If you remember in the infinite case, if you have an infinite box, then it was just this, right? It really reached 0 on one side and 0 on the other. Now, because the box is finite, the wave function can decay a little bit outside. So there's some probability if you measure this particle to find it outside the box, but it's small. And it gets larger as the energy increases, of course, because then it has more energy to go past this barrier until finally we're out of here. And you have just scattering states. So if you want the exact form of the scattering states, they are very similar to what we did in the lecture. And I think there was one exercise in the tutorial where the last part of the exercise asked, look at the reflection coefficient cases for scattering barrier in the case where this barrier is negative, where V0 is negative. So that's an example, an explicit example of this. Okay, so that's all I wanted to say for the finite box. You can, of course, compute the exact wave functions if you want. I don't think it's something I'm going to ask you, but at least it gave you an idea of the kind of tools we can use and the kind of restrictions imposed by quantum mechanics, right? Good, so that's it. And now, in a while, I will record the other lecture, which is on harmonic oscillator. Let's see if I can do it today. I don't know. Okay, so thank you so much.